Okay, so we're going to take a little bit of a look at how our periodic table came into being, how it came from nothing to what we see today in front of us here. Okay, so we're going to start off and talk about some of our important scientists again, what developments, what contributions they made to the periodic table. And our first scientist we're going to talk about is a guy we've talked about before quite a few times, Antoine Lavoisier. Now, Lavoisier really in this case is one of our very first scientists who tried to do some type of classification of the elements. He tried to group them. And he's really the first one who tried to do this. But the question is why? Why would we try and group the elements anyways? Well, the answer is pretty simple. It's a lot easier to take a look at elements and look for similarities and look for properties and find out new information if you have a nice order to something. Can you imagine going in the library and being asked to find a particular book and not having that book be anywhere in a particular order? It could be anywhere in the entire library. Wouldn't be very fun, would it? Classification and order is a very useful thing for us. So it's a lot easier to see and to study relationships if you have that order to the elements. Plus, you start noticing relationships, you can find out a lot more information from that. So he's the first person. And really what he did is he grouped the elements that were known at the time of that he was around into 4 different groups or 4 classes. And here are those classes. He named them as gases, metals, nonmetals, and earths. And as you look at some of the elements in here, you're going to see that some of these things are definitely not elements like light and heat. And some of them have really weird names, the phlogisticated air, inflammable air, which are actually different elements. Metals, which most of these are metals. So 1 or 2 of them are not. Antimony and arsenic are not metals. So he didn't have his groups all, and his elements all correctly in the right groups. And his nonmetals, some of them don't even have names in the English language. But he started to take what they thought were elements and organize them, and that was a big first step. So some elements, a lot of elements were missing. Every element on the table isn't here because they weren't known at that time. And some of the ones he had aren't elements. But it's a big important first step in trying to find out more information about the elements that are around us and knowing about them. Okay, our next scientist was an English scientist by the name of John Newlands. And you can see John Newlands over here in the top right-hand corner. And what Newlands did was he took the elements and he arranged them in atomic mass order. And not only did he arrange them in atomic mass order, he also took the list of those elements and ended up wrapping them around a cylinder. And when he did that, he saw something like in this picture. And when you look at that picture, you notice that he noticed something pretty unique about the elements. That when he wrapped that list around the elements, around that cylinder, elements with similar properties were in the same column. They were repeating themselves. And what he noticed is those elements tended to look like they repeated in units of 8. So you can see here on this list of notes here and he called those octaves because octaves occur every 8 notes. You have the next octave. And so he called this the law of octaves. Elements are repeating in these groups of 8. And hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And then you saw repeating patterns. You get the chlorine. Okay, and elements lithium and sodium were 8 apart. Beryllium and magnesium were 8 apart. So we saw that repeating pattern. But there were some problems. They didn't always happen that way. Like cobalt and nickel here, they did not have the same or continue in that pattern. They repeat themselves back and forth. So something was wrong here. And that was one of the biggest reasons, besides the fact he decided to use a musical term, octaves, to describe what was happening. And that really caused his ideas to not be accepted right away at that time. But there's a repeating pattern to our elements. Hans Dobereiner, a German scientist then, as our next scientist, who was looking at elements that are called triads. And all a triad is, it's a group of 3 elements that have similar properties. And what he noticed about those groups of elements that had those similar properties was that the middle element of those 3, the middle mass element, that mass was the same or very close to the same as the average masses of the heaviest and the lightest. And you can see that here in this example. Like we take one of our sets of triads, lithium, sodium, and potassium. Lithium has a mass of 7. Potassium is 39. 7 plus 39 divided by 2 is 23. Sodium is 23. So he's looking at some really different values in this case. And the same was true with atomic numbers. The atomic numbers averaged ended up being the same as the middle element as well. But again, remember, these are all groups of elements that had similar properties to each other. But an important step, say, hey, something is going on here. We're seeing something happening. We're seeing similar properties occurring. And without any kind of order, we won't notice any of these things. Next up, we have Dmitry Mendeleev, which a lot of times we can call him the father of modern chemistry, because he really does something new and unique. And even though we should give another guy by the name of Meyer, Hans Lothar Meyer, some credit as well, he didn't get published first, so he doesn't get as much credit. But he came up with our first idea of what a modern periodic table should look like. He's the very first person to do something no one else had done before. And as he arranged elements not only in increasing atomic mass order, but also by properties. Something a little bit different. He had elements in a column with the increasing atomic mass and in rows that had similar properties to them. So on the left-hand side, you can see it's even in Russian, some of it up here. You can see his elements. You can see hydrogen, beryllium, boron, carbon, nitrogen, oxygen, fluorine. That's our first column on the table, or first row on the table. And their atomic masses in this case. Similar properties went across the row. Now, two significant discoveries came about when he did these two things. The first one is he kind of confirmed what Newlands had said. There is some periodic pattern happening. And he came up with something called the periodic law, which says the chemical and physical properties of the elements are a periodic function of the element's atomic masses. Now, what does that mean? It just means that the properties of the elements are repeating each other in a particular pattern based on the atomic masses. Pretty simple. Now, the second thing, which is very significant as well and really helps legitimize his table, is that he noticed that he had to leave some spots on the table and leave a gap in it. To get an element to the next element, which he would fit in the gap, he had to leave a gap or leave a couple of gaps between it to get it to line up in the same properties. You can see right here zinc, then he has two question marks, then arsenic. He had to leave two blanks here to get arsenic to line up. Now, arsenic was the next one in line, so it would fit in here with boron and aluminum, but it doesn't have those properties. It has properties like sulfur and phosphorus. So not only did he predict, then leave those gaps, he predicted that there had to be some unknown elements there that we did not know about yet. And not only did he predict that the elements would exist, he predicted what their properties are going to be. And it wasn't until in a couple of cases here, 25 or 30 years later, before those elements were discovered, and they did have the properties that he predicted. It was really close to what they were. In fact, some of those elements he predicted, we should see on this slide, were scandium, gallium, and germanium. Now, I didn't put them up there, but that's what they were, scandium, gallium, and germanium. And they were found 25, 30 years later to have those same properties. But his table is legitimized, and the periodic looks, hey, yeah, this all looks pretty good, and it really seems like it works real well, but there was a problem. And that problem that he couldn't explain was some of the elements were out of order. The elements didn't always follow an atomic mass order. He had to have the atomic masses switched around for a couple elements. And he couldn't explain why that would be. So it didn't make much sense to have an increasing atomic mass order, but then have some masses backwards. Well, that was discovered and explained by a scientist in the early 1900s by the name of Henry Moseley, an English scientist. He solved that problem. He's the guy, and we've talked about him once before, he's the scientist who found out the number of protons in the atom, which we call the atomic number. And when we arrange the elements in atomic number order, that problem of Mendeleev's elements out of order takes care of itself. We can say this is why they should be in the order, why the lighter element should be after a heavier element, because it has actually more protons in it, less neutrons. So it's that number of protons that determines what the order is. And our periodic law then was changed to reflect this fact. The periodic law now says the chemical and physical properties of the elements are a periodic function of the element's atomic number, how many protons there is, not by the mass of the elements. Well, that takes us up to our modern periodic table. I've got to wave my arm a little bit, get the light to come back on. Stand up. Sorry about that. And our modern periodic table has a couple of characteristics that we just want to pay a little bit of attention to quickly. First of all, it's arranged in increasing atomic number order going across left or right in the table. But it still follows a pattern of Mendeleev's table that when you take a column on the table going up and down, those elements will generally have similar properties. Rows in a periodic table are called a period or a series, and there are 7 of those. And each row is a new energy level, like we saw in our last chapter. And columns are called families or groups. Called families because they have similar properties. So elements have similar properties, they're related, you're a family. If we take a look at our modern periodic table, a couple of the keys about it, if we look at some of the groups, some of our groups have names. Now, there's going to be some significance here to these numbers 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. There are going to be some significances. We'll talk a little different time about that. But some of our elements here have some different names to them. Now, if we take the S and the P block on the periodic table, which is the first 2 columns, and then the elements on this end, those are what we call the representative elements, or main group elements. And that's just because those are the elements that have that outer shell being filled by the S and P orbitals. Okay. But group 1, that first column on the table, lithium, sodium, potassium, rubidium, cesium, francium, is called the alkali metals. They're the most reactive metal on the periodic table. Group 2, beryllium, magnesium, calcium, strontium, barium, and radium, are the alkaline earth metals. Group 7, starting with fluorine, is the halogens. And group 8 is the noble gases, the elements that do not react with anything else.
To the high school office. One guy to the high school office.
The D block on the table are called the transition metals. This is because we're seeing a change in properties as we go across. The F block metals are the rare earth metals. In fact, we have 2 series which have names. The only 2 series in the whole periodic table have a name themselves, the lanthanide and actinide series. And again, what's different about the F block elements, the rare earth metals, is that similar properties occur here in the row, not in the up and down. So the lanthanide series, these elements are all similar. In the actinide series, these elements are all similar. That's a little bit of difference. Another key point to notice about our modern table then is a stair-step line that you see on many tables. I've made it in black here to be a little thicker. That's a dividing line. Left of that line, you may have noticed that we had alkali metals, alkaline earth metals, transition metals, rare earth metals because they fit in right here. And then aluminum, gallium, indium, tin, lead, bismuth, thallium. These are all metals. So everything left of that stair-step line is a metal. Everything on the right of that stair-step line is a non-metal. And right along the line, boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and acetine are semi-metals or metalloids. Now, what's the differences in these? You can see that over here on the left-hand side. Metals do things like conduct heat and electricity. They're malleable, which means you can pound them into thin sheets. They're ductile. You can draw them into thin wires. They have luster. They're shiny. They're generally going to have less than 4 valency electrons in them. Going to be significant later on. Nonmetals are insulators. They don't conduct heat or electricity. They're brittle. They're not malleable or ductile. They're brittle. You hit them with a hammer, they're going to break instead. They're generally going to be, a lot of them are going to be gases or dull solids. They're not going to have luster. They're also going to generally have more than 4 valence electrons. For those metalloids, those elements right along the stair-step line, those elements are going to have properties of both metals and nonmetals. For example, silicon is a non-metallic metalloid. That means it's going to be, since it's on the non-metal side of the stair-step line, it's going to be more non-metallic. It doesn't have a lot of luster. It has a little bit of luster. It's kind of dull. It's not malleable. It's not ductile, but it does conduct electricity somewhat. It's a semiconductor. It does conduct electricity to an extent, which is why they're using computer chips. So right below it, germanium is also a semi-metal, but since it's on the other side of the stair-step line, it's going to be more of a metal with some non-metallic properties. Okay, so how those properties are acting depends on where they fall within the table. Okay, and that should do it for our development of the periodic table and where we are today. And we'll be talking more later about significance of these numbers, what those numbers are going to mean for us, why they're going to be important for us, and also look at trends on our periodic table and classification of more of our elements.